Welcome to this video lecture on calculating the change in specific entropy for an ideal gas. In prior video lectures, we talked about how to calculate the change in entropy for real substances. In that case, you would use the property tables. And we had different ways to calculate entropy from those property tables. For example, if you were dealing with a saturated liquid vapor mixture, you would use the quality like we've used before to calculate specific volume and specific internal energy, etc. So the same sort of thing for specific entropy. For compressed liquids, we had this approximation for calculating the specific entropy for a compressed liquid. It's about equal to the specific entropy for the saturated liquid at the same temperature. And then in the last video lecture, we talked about the change in specific entropy for an incompressible substance. That's useful for dealing with liquids and solids. We started from the TdS equations and derived an expression for an incompressible substance. And then today we're going to talk about using the TdS equations to get the change in specific entropy for ideal gases. Why don't we go ahead and take a look at the screen, and you'll see a picture. It's kind of an interesting photograph of two T-38 supersonic training aircraft. This is an actual photograph. The color's been enhanced, but it's an actual photo of these aircraft flying in the sky. The distance between them is about 30 feet, according to the information that came with the photo. And they're flying at supersonic speeds, and what's striking about the photograph are the colors around it. You see all these different colors, and in particular these kind of black lines that emanate from surfaces on the aircraft. The colors here correspond to the gradient in the air density flowing around it. It comes from a technique called Schlieren photography. It's not something we'll cover in this course, but if you do any course on compressible gas dynamics, compressible fluid flow, you'll talk about Schlieren photography, at least at some point in that course. But it shows where the air density is changing very rapidly. And you'll see, like here, for example, you get this rapid change in air density, and that's what's called a shock wave. So shock waves show up when you deal with supersonic flows that are faster than the speed of sound in that substance. It's a topic that's covered in compressible gas dynamics. Across a shock wave, you get very rapid, essentially step changes in properties. So you'll see a sudden increase in the pressure of the air going across that shock wave. That gives rise to a sonic boom that people hear, that just the pressure changes very rapidly. You'll get a rapid increase in the temperature, rapid increase in the air density, and a rapid decrease in the air velocity. So these shock waves are very important phenomena in compressible fluid flow. One of the other things that you'll find if you study shock waves is that you get a change in entropy. The entropy actually increases across the shock wave. And the way that you calculate that entropy increase is actually using the relations that we'll derive in today's class. So what we're learning today in our introductory thermodynamics course actually is useful when you start analyzing high-speed flows of compressible gases like air across a high-speed aircraft. And in particular, this change in entropy equation that we're going to derive is used to analyze the change in entropy across a shock wave like right there that I've drawn on the screen. By the way, if you want more photographs that look really interesting, these Schlieren photographs, I encourage you to go to this website. This is where I got this particular photo from, and there are lots of other photos available on the web. So if you like this kind of photography and some interesting things with air density, etc., take a look on the web. You'll find lots of other kinds of photos. So let's go ahead and get into the material. We're going to start with the TdS relations, just like we did for the change in specific entropy for an incompressible substance. So we're going to start with these. And remember, by the way, the TdS equations are just equations that relate properties to one another. So it relates temperature and specific entropy, specific internal energy, specific volume, pressure, specific enthalpy. It's just a way to relate properties to one another. And they're general. These equations are general equations. They're not specific for incompressible substances or ideal gases. They're just general. And what we're going to do is take these general equations that relate properties and then combine them with our specific expressions for an ideal gas model. We have, of course, the ideal gas law, which we can differentiate both sides to get this kind of expression. We have a couple of other expressions that relate properties. So this one relates the change in specific internal energy to temperature. The CV here is the specific heat at constant volume. That's in general a function of temperature. And then here we have specific enthalpy is equal to the specific heat at constant pressure, which is in general a function of temperature, times small change in temperature. So we have these relations are specific to an ideal gas. And what we're going to do is we're going to substitute them up into here. to get a couple of different expressions. So we're going to start first with this left-hand TdS equation. I'm going to rewrite it. And then for the du, I'm going to substitute in Cv dt here. Cv is a function of temperature in general, so I'll keep that parentheses t there just to make that explicit. And then for the PDV, I'm going to make use of the ideal gas law right here. I'm just going to substitute in for that. So that'll be equal to R dt minus V dP. So that quantity in parentheses is just coming straight from here for the PDV term. And then let me do a little rearranging. So we'll have Cv plus R times dt is equal to minus V dP. And then what I'm going to do at this point is I'm going to take the ideal gas law right here and just rearrange it for the V. V is equal to RT over P. And then I'll substitute that expression in right here. So this will be CVT plus R dt minus RT dP over P. Now, what I'll do is I'll divide everything through by the temperature, so I'll have ds is CVT plus R dt over T minus R dP over P. And then the last thing I'll do, well, second to last thing, is the Cv plus R, that's equal to Cp, the specific heat at constant pressure, which in general is a function of temperature. Recall from the ideal gas model, we also had that Cp minus Cv is equal to the gas constant. And by the way, that gas constant is the gas constant for whatever substance you're dealing with. So it'd be like, for example, the gas constant for air or the gas constant for carbon dioxide. It's not the universal gas constant. Okay, so then finally we get ds is equal to Cp times dt over T minus R dP over P. And we can integrate both sides of that equation, and then we'll be left with delta S, which is just S2 minus S1, is equal to the integral from T1 to T2 of Cp dt over T minus the gas constant. It's a constant, so it just comes straight out of the integral. And then I'll have the integral of dP over P, which is just a natural log. So this will be natural log of P2 over P1. And that gives us a relation between our specific entropy change and changes in temperature and pressure. So this is now a useful relation we can use for ideal gases. If we need to calculate a change in specific entropy for an ideal gas, and we know how the temperature and pressure change, then we can make use of this expression to relate them. Okay, so again, it's just combining the TdS equation with expressions for an ideal gas. Now we can do this again, but now let's make use of the other TdS equation. So I'm going to do that right over here. So TdS is equal, instead of dH, the change in specific enthalpy, I'm going to just make use of our expression for an ideal gas over here. So that'll be Cpt dt. And then again, instead of writing minus PDV, I'm going to go ahead and make use of this expression here. You know what, this expression is incorrect. I just realized that. That should not be minus PDV, that should be V dP. Sorry about that, I need to make that correction. So what I'm going to do is make use of this expression here for that one. I just have my TdS equation incorrect. So I'll make use of this with that. And then that becomes, let's see, a plus, oh, I'm sorry, this will be a minus R dt plus PDV. Okay, so what I've done is I've just taken this expression, substituted it in here, and that's what I get here. Now let me go ahead and combine some terms again. Cpt minus R times dt. And then instead of PDV, I'm going to again make use of the ideal gas law. I'll just rewrite that as P is equal to RT over V. And I'm going to substitute that in right here for that P. So I'll get plus RT dV over V. Again, divide through by temperature. And then notice that Cp minus R up here is just going to be, Cp minus R is just going to be Cv. So then this becomes ds is equal to Cv, which is in general a function of temperature, times dt over T, plus R dV over V. We can integrate both sides, and we're left with delta S is S2 minus S1 is the integral of CV t dt over t. So go from T1 to T2 plus R times the natural log of V2 over V1. So this is a second expression that we could use for relating the change in specific entropy to changes in temperature and specific volume. So we could use either one of these. It's just relating different properties to one another. These two are connected to one another through the ideal gas law. Okay. So anyway, those are now useful expressions that we can use to calculate changes in specific entropy. Just like what we did for the incompressible substance model. We used a derivation to get the change in specific entropy in terms of temperature in that case. Here it's either temperature and pressure or temperature and specific volume, for example. Now, when you look at these expressions, they're all fine and such, but you would have to do this integral of Cp dt over T as we go between the different temperatures, or Cv, integrating that expression as well. That's inconvenient. We don't like to do that. We'd have to find an expression for how the specific heats change with temperature and then substitute it in here and do that integral. It's tedious. We don't want to do it. So what we can do is we can actually pre-calculate what those integrals are. We can take into account the variation in the specific heats with temperature, do that integral, pre-calculate it, and put it in a table, and then we can use it. So we're going to define a new property. We'll call it S superscript 0 here. I'll just call it S naught for convenience. It's not a specific entropy. Historically, they use the symbol S superscript naught, but it's not an entropy. We probably should have used a different symbol to avoid confusion. But I'm going to define it. It's going to be a function just of temperature, and it's going to be defined as the integral from some reference temperature to some final temperature of Cp t dt over T. So it's basically going to be, it's this kind of integral right there, except the only difference is that I'm leaving the upper temperature just arbitrary, and the lower temperature is just some reference. It doesn't matter what the reference is, and I'll explain why in a moment, but it doesn't matter what that lower reference temperature is because it ends up subtracting out. For example, if I wanted to calculate that integral, let me just go ahead and show it to you. That would be like the integral from our reference temperature to T2, or actually, yeah, let me write it this way. It would look like this. All right, so I could do, if I wanted to calculate this integral from T1 to T2, I could start from my reference to go up to T1, and then I could do subtract out going from the reference to T1. So here it's T2, here it's T1, and then that'll end up with that kind of limit, right? So it really doesn't matter what the reference temperature is because it just gets canceled out. So then this ends up looking like S naught evaluated at T2 minus S naught evaluated at T1. Okay, because that's how I've defined my S naught. You can see it here. So we can go ahead and pre-calculate those integrals. So I could pick some arbitrary reference temperature, find the Cp as a function of temperature for whatever substance I'm dealing with, like air, for example, and then just do this integral for a whole bunch of different temperatures and put it in a table. And that's exactly what's done, and I'll show that in just a moment. But then what happens is our delta S, we're specifically focused on this left-hand expression, just becomes S naught T2 minus S naught T1 minus R natural log P2 over P1. So that's what this expression becomes. And then these are found in an ideal gas table, and I'll show you that in a moment. Okay, so we just pre-calculate those integrals and throw them into a table. And here's an example of one of those tables. Here's the ideal gas table for air. And you notice that these are just functions of temperature, right? So here's our ideal gas table for air. Remember that the specific enthalpy, specific internal energy were just functions of temperature for an ideal gas, right? Well, it turns out the S naught that we have here is also just a function of temperature. So these are found right here in this column. of the table. So that's how we find those. And then, of course, the gas constant, we can always look that value up. And then the pressures, normally you would know. By the way, these should be absolute pressures when you evaluate this. So make sure they're absolute pressures. When you take the ratio of two pressures or the ratio of two temperatures, they need to be absolute pressures and absolute temperatures. So this gives us an even more convenient way to find the change in specific entropy. We no longer have to worry about doing this integral here. We can just look up values in a table for that. So these expressions I have here are for ideal gases. And they take into account the variation in the specific heats. Now we don't have a similar expression for the integral of CV dt over t. And that one's not used quite as much, so we don't have that expression. Instead, we just have the one for the CP. And again, the S naught here is not a specific entropy. It's just some other quantity. It's related to specific entropy, but it's not a specific entropy by itself. What it is this integral. So we probably should, like I said, we probably should have used a different symbol than S naught, but just historically, that's the symbol that's been used. Okay, so that's pretty convenient to have. Now, let's say we had these expressions here and we were dealing with a small change in temperature. In that case, the variation in the specific heats may not be all that much, and we could assume that those specific heats are nearly constant. We call that kind of substance a perfect gas. It's an ideal gas with constant specific heats. And in that case, what we can do is we can pull the CP and the CV outside the integral because we're assuming they're constant. And then you'd just be left with the integral of dt over t, which would be a natural log of t2 over t1. Same thing over here. So we could rewrite these two expressions for a perfect gas down here. Let me put it on this side. So for a perfect gas, and a perfect gas, again, is an ideal gas with constant CP and CV. Again, it's pretty good. It's another approximation. It's another level of approximation. In general, we know CP and CV are functions of temperature, but if the temperature range isn't too big, and too big depends on what kind of material you're dealing with and what the temperature, what the temperatures are. But as a kind of an engineering rule of thumb, if you're dealing with less than maybe 100 Kelvin temperature variation, maybe 200 Kelvin, assuming constant specific heats is probably reasonable. But again, you have to be careful. It depends on the substance you're dealing with and the exact temperature you're dealing with. But if you assume those specific heats are a constant, then we can pull these constants. We can pull the CV and CP out of the integral because we're assuming they're constant. And then what we're left with is delta S is equal to CP, natural log of T2 over T1, minus R, natural log of P2 over P1. And delta S is equal to CV, natural log T2 over T1, plus R, natural log V2 over V1. So these are for a perfect gas. Okay, so again, these come directly from here, assuming constant specific heats. So you have to keep in mind what the assumptions are in using these equations. First of all, everything here is involving an ideal gas. So don't use these for incompressible substances or water or changing phase or anything like that. These expressions here and here are for an ideal gas. It takes into account the variation in the CP and the CV with temperature. But if the CP and CV variation isn't very much, you assume those are constant, and then you have this expression for a perfect gas, so ideal gas with constant specific heats. It's just a little more convenient to work with. You don't have to look up anything in a table. It's just easier to work with, and so many times we'll assume perfect gas behavior when we do hand calculations where it's just easier to do that sort of thing. These expressions will be a little less accurate than this expression here, for example, because we made that additional approximation. So just be aware of that. Okay, the next thing that we're going to do is we're going to say, let's say we're dealing with an ideal gas that's undergoing an isentropic process. So now let's assume that we're dealing with an ideal gas and an isentropic process. Remember that an isentropic process is one where the entropy change is 0, right? The entropy doesn't change. In that case, what I'm going to do is just go back up to this expression here, and let's go ahead and use this one. Then I'll just set this left-hand side to 0, and then what I'm left with is the following. So 0 is equal to S naught T2 minus S naught T1 minus R natural log P2 over P1. Let me do a little rearranging here. So I'll have natural log P2 over P1 is equal to S naught T2 minus S naught T1 divided by R. And then let me take the exponential of both sides. Okay, so we're there. And then let me do one more step. I'm going to carry the exponential through, so it'll be like exponential of S naught T2 all over R divided by exponential S naught T1 over R. Okay, so I'm to that point so far. Again, all I did was I went back to this expression for an ideal gas, and then just set the left-hand side equal to 0, and then just did some algebra to get to that point. Now again, you could look up the S naught value at T2 and T1 in a table and evaluate, divide through by the gas constant, take the exponential of it, and then you can find the change in pressure for that. We can do that. It's kind of several steps. Engineers tend to be lazy. We don't like to do that. So let's go ahead and define a new quantity, and we'll call it P sub R. Let's just call it the exponential. And by the way, that P sub R is a function of temperature. Let me just make that explicit here. So it's the exponential of S naught at the temperature divided by R. Now this P sub R is not a reduced pressure. It's not, if you recall back when we talk about ideal gases, there's a thing called a compressibility factor. It's the symbol Z. It's a compressibility factor that's used to determine whether or not a gas can be assumed to be an ideal gas or not. There was a plot. Let me just kind of sketch it out for you. If you recall, there was a plot that had Z, that's the compressibility factor, as a function of P sub R, which was defined as the pressure divided by the critical pressure. And then you had all these kind of curves. And these were T sub R, which was defined as the temperature divided by the critical temperature. Unfortunately, we're kind of reusing a symbol here. This P sub R and this P sub R are not the same. So let me highlight that. Not the same. Okay, this is called a reduced pressure here. This is not a reduced pressure. This is just something else. It's called P sub R. Again, it's unfortunate the choice of symbol that's commonly used here, but it's just a different quantity. This P sub R is just the exponential of this S naught over R term. Okay, so it's completely unrelated to that. But what we can do is, since we've already tabulated this S naught quantity, we could go ahead and also tabulate S naught divided by R, take the exponential of it, and put that in a table. Okay, and that's given right here. You can see, again, this is our ideal gas table for air. Here's the P sub R. It's just taking this column divided through by the gas constant, take the exponential of it, and then you end up with that. And what's nice about that is if you expand this equation using our definition, you get P2 over P1 is now PR T2 over PR T1. So that gives us a really quick relationship between pressure and temperature for an ideal gas in an isentropic process. Remember the assumptions here. This is ideal gas and isentropic process. You have to have both to use this expression. Okay, so that's a pretty fast relation to use. It's very convenient. You can just look these up in a table very quickly. The pressure's here. It's very easy. Again, make sure these are absolute pressures. It just makes it very easy to work with. But it's specifically for an ideal gas undergoing an isentropic process. It already takes into account changes in specific heat with temperature, so that's all built into it. And because it's built into it because the S naught does the integration of that, and that's built into it. So it's very convenient. And you can do a similar thing. I'm not going to do the derivation for it, but you can do a similar thing for the specific volumes. For the expression with the specific volumes, you can get something that looks like this. If you want to see how what the derivation for this is, you can go ahead and look at my book style notes, but you'll get another expression relating specific volumes and temperature. This one comes, again, I won't do the derivation, but it comes from this kind of expression right here. And this is, again, for an ideal gas undergoing an isentropic process. The V sub r, it's not a reduced specific volume, it's just a V sub r. It's a function of temperature, and it's also pre-calculated for you. It's right here in this column. Okay, just like P sub r, we have V sub r here. So this is not a specific volume, it's just a function of temperature. It's just an unfortunate choice of symbols. But this gives us a nice relation between specific volume and temperature for an ideal gas in an isentropic process. Let me erase that line. So both of these are for an ideal gas undergoing an isentropic process. Now let me consider the case where we're dealing with a perfect gas undergoing an isentropic process. In that case, we're dealing with these equations because it's a perfect gas. And if it's isentropic, the delta S is 0 there. And so we can do some rearranging of these. And let me just write that one down here. So for that case, P2 over P1 is equal to T2 over T1 raised to the K over K minus 1 power. We also have V2 over V1 is equal to T2 over T1 raised to the 1 over 1 minus K. And then you can combine those expressions together to get P2 over P1 is equal to V2 over V1 raised to the minus K. These expressions are for a perfect gas and an isentropic process. Okay, so I'm not going through the full derivation of that, but what it is just taking these expressions, setting delta S equal to 0, and then doing a little bit of rearranging for that. Okay, and that's how you end up with these. The K's here, by the way, are the specific heat ratio. So K is defined as Cp over Cv. It's called the specific heat ratio. The specific heat ratio for air, for example, is pretty close to 1.4. That's a good number to remember. So that's what these K's are in this expression. So this set of equations is, again, very convenient to work with as long as you're dealing with a perfect gas, so an ideal gas with nominally constant specific heats, meaning the temperature range isn't too large, and in particular for an isentropic process. Okay, so these are only for isentropic processes. So we've covered a lot of different equations. It's very important to just keep in mind what assumptions went into them. Okay, so these are just, again, for an ideal gas, no assumption about this specific heat, no assumption about it being isentropic or not isentropic, it's just delta S here. These are for a perfect gas, so an ideal gas with constant specific heats. Again, it can be used for whether it's isentropic or non-isentropic. These are for ideal gas and isentropic, and these are a perfect gas and isentropic. Now I keep saying isentropic. Why do we care about isentropic processes? So let me just say a few words about that first. We assume many types of flows to be isentropic. So one example of which is, let's look at the flow through a nozzle. So let's say we have some air flowing at high speed through a nozzle. And what you'll find actually from fluid mechanics course, it's outside the scope of the current course, but in a fluid mechanics course, what you'd find is that there's a layer very close to the boundaries known as a boundary layer. It's imaginatively named. And in that boundary layer, you get very large velocity gradients. So I'll just kind of sketch it like this. So we have very thin layers. These layers are called boundary layers. And in those boundary layers, you get very large changes in velocity. It basically goes from 0 velocity at the walls of the nozzle. It's called the no-slip condition. The fluid sticks to the walls. So 0 velocity at the walls up to a very high speed just outside the boundary layer. So you get a big change in velocity over a very small distance. Those large velocity gradients lead to a lot of energy dissipation. You have, in a fluid, you have a property known as viscosity. You probably have heard the term viscosity before. It's kind of a measure, it's kind of like the internal friction coefficient of a fluid. If you have something with a high viscosity, it means that you can dissipate a lot of energy in that fluid. Like honey has a high viscosity. If you pour honey out onto a surface, it doesn't flow very fast out to the sides because viscosity slows that flow down and dissipates a lot of energy very quickly. If you poured water, it has a lower viscosity. It'll spread much faster. Okay, so when you have viscosity coupled with a large change in velocity, you get a lot of energy dissipation. So in those red regions here, those boundary layers, you get lots of energy dissipated. Outside of the boundary layers, the velocity gradients are pretty small, and even if you have some viscosity, it doesn't play as much of a role. The energy dissipation is related to the viscosity times the velocity, a function of the velocity gradient. So if the velocity gradient is pretty small, you don't have very much energy dissipation. So actually inside here, there's very little dissipative kind of behavior. It's essentially an internally reversible flow in this region. So in here it's like, let me put it in blue. Here it's internally reversible flow, whereas in the boundary layers we have it's internally irreversible because of the action of viscosity. Okay, so where the irreversibilities are is very concentrated. Now in addition, in many of these flows through nozzles and other kinds of devices, there's not a lot of heat transfer across the boundaries. The temperature change, the temperature difference from the inside to the outside is usually not huge. The surface area usually is not all that big, so there's not a lot of surface area through which to conduct heat. And oftentimes there's some matter of insulation on these surfaces that helps reduce heat transfer. So we often assume that these flows are both adiabatic, because there's very little heat transfer, and most of the flow is actually internally reversible. So if it's adiabatic and reversible, that means it's isentropic. Again, it's not totally reversible, but the boundary layers are pretty thin on those surfaces, so most of the flow is really reversible. So we can model the flow through this device as an engineering model, an approximation to reality. We can model it as being an isentropic flow. And if it's isentropic flow, let's say we have air flowing through it and it's isentropic flow, then we could use these kinds of expressions here to relate the properties through that nozzle. That's pretty powerful and it's very convenient. It's something you will do if you continue with fluid mechanics and kind of a higher level course. But that's one of the reasons why we care about isentropic processes, is because we use them as a model for real life. Oh, there's one last comment I want to make before we close, and that is this expression for this perfect gas isentropic process. If you look at that for a moment, you'll see that actually looks like PV raised to the K is equal to a constant. It's like a polytropic process. Now early on, I think I may have mentioned in some earlier video lecture that we care about polytropic processes because there are many processes that look like PV raised to the N. It's equal to a constant. So for example, if you're dealing with an ideal gas undergoing an isothermal process, you would have PV is equal to RT, which would be a constant if it's isothermal. So this is ideal gas and isothermal. Then it'd be PV is equal to a constant where the power exponent is N equals 1 in that case. So that's one example of a polytropic process. It's not uncommon to see that. But here we have, if we have an ideal gas, actually it's a perfect gas, undergoing an isentropic process, then we have another polytropic process. So here our power exponent would be K. So that's another example of a polytropic process. I just wanted to highlight that because we spent quite a bit of time talking about various polytropic processes. Why do we care about them? Well, it turns out that they're not uncommon to see. When you're dealing with an ideal gas undergoing isothermal or maybe isentropic conditions, we have what appear to be polytropic processes. So I just wanted to highlight that. Okay, I think that's everything I wanted to cover for this video lecture, so we'll go ahead and end it there.